All right, let's get started. It's my pleasure to introduce our next speaker. And it's the founder and CEO of Deepen AI, Mohammad Musa. And his background is in products. He has worked at Google. He has worked at Xilinx, my current alma mater. And he's going to be speaking to us about using LiDAR for machine perception. Mohammad?
Is anybody using LiDAR already? Okay, we have a few. Awesome. Well, cool. Hopefully you'll learn something new today, even if you're using LiDAR. Just a little bit about us at Deepen. We call ourselves, we're trying to be a picks and shovels of autonomy company, building tools and infrastructure and services that are required across the autonomous stack. So we don't build any autonomous products ourselves, but we help our customers do that. And we have 3 products. One of them, Eve over there, is a fuse sensor platform. So we can annotate LiDAR, radar, camera, sonar, and other types of sensors in a cohesive way. And you can generate training data. It uses a lot of sensor fusion and AI inside of the tool to make the process much faster and much more accurate. We'll skip talking about the 2D products for now, because I think it's not too relevant for the audience if you care about 3D perception. Cool. So there are a lot of depth sensors, as we all know, from structured light to time of flight, stereo cameras, sonars and radars, like I mentioned, and now LiDAR. The slide is a little bit busy. I tried to add a visual for every type of depth sensor that we have. And now when LiDAR came along, it's really, I would say, now a very old technology. You know, when lasers were first invented, one of the first use cases was for mapping the moon or understanding the geospatial properties of the moon. And they used the LiDAR to do that. And since then, it was mostly used for planes carrying the LiDAR to understand geospatial use cases. And then in the DARPA challenge back in 2005, the Velodyne CEO was participating, and then he said, well, let's use these Velodyne hardware that was for acoustics, and they converted it to do LiDAR properties. And we got that first mechanical LiDAR that most of you have seen on the older Google cars, and now pretty much a lot of the manufacturers are still using Velodyne, but there are more, maybe there are 40, 30, 35 plus LiDAR startups out there that are competing on different aspects of their technology. LiDAR stands for laser detection and ranging, and it fires laser beams in as many directions as it can. If it's a mechanical one, it would do a 360 degree. If it's a flash LiDAR, then it will have a smaller field of view. And it uses some of the typical depth measurement approaches, time of flight. Not all LiDARs use that, but that's the most typical. And if you have the light beams very well collimated, that can give you a much better location accuracy and depth accuracy. What you get back in response after you get these reflections of the light, you can formulate. Sorry? Oh, okay. You can formulate an XYZ 3D point cloud. You get the XYZ coordinates of everything. You can measure velocity using LiDAR. However, it depends on what type of LiDAR technology you're using. The accuracy of the velocity you're getting back may or may not be as good as what you get from a radar. And I think we'll talk about some of the differences between radar and LiDAR later on. But keeping in mind, radar doesn't do a great job with static objects, while LiDAR does a great job with any object, whether it's dynamic or static. And the other differentiation between radar and LiDAR technology is that the location fidelity of your understanding of the exact location in 3D space is much better when you have a laser as your sensor. While radar can kind of give you estimates and you need to do some math, and that math is dependent heavily on what the radar provider is giving you. So a continuation of how it works is essentially you use light. Was talking earlier with Oryx Vision over here. They use a very wide wavelength light, like a 10 micron, that is very safe to the eye. But a lot of people, there is a range from like 509 nanometer to 1550 nanometer, and different power that the light carries. Some of it, especially on the 509, it will actually end up in your retina. And so your eye will be able to absorb it. And if it carries a lot of power, you can actually get affected. So there are concerns about eye safety depending on the wavelength of the light and how much power it carries. But it also depends on kind of the use case. The typical composition, I guess, you have transmission, you have reception, and you have a lot of stuff that goes along with it. I think that's kind of a good summary. But in each piece, there are startups that are trying to innovate in all of these aspects. So like you'll have some companies trying to innovate on the light technology itself, others on how you can scan it, and the photo detectors or diodes. Like Oryx was just telling me that they use a very special antenna that is much cheaper than the diodes that are typically used for other LiDARs. And especially for geospacing, for geospatial use cases, they always have to couple it with GPS and IMU, because they use that to triangulate the point cloud that they're collecting. And obviously, you need a bunch of control hardware. So typically, you want to have very short pulses. The shorter the pulse, the better resolution and accuracy that you're going to get. And what you have in, maybe I'll talk about it in the next slide. But anyway, let's kind of continue. So depth resolution will depend on your receiver sensitivity and material. Obviously, you divide by 2 because the light has to go hit something and come back. And there is always a constant, we talked about, sorry. And the delta t is the time difference, and c is speed of light. And you get a ton of variations from different frame rates, different ranges, different resolutions. And because most of us are familiar with the Velodyne LiDARs, they have like Velodyne 16, 32, 64, and 128. That's the number of laser beams that are rotating in those mechanical LiDARs. And the more beams you have, obviously, the higher density you can get, and the higher likelihood that you're going to catch everything that is around you. If you had only 4 beams of light coming out, and if I direct those 4 beams and rotate, I will miss, depending on how much spacing in between and what are the angles that are coming out. So the resolution will get affected, obviously, by the field of view and the orientation of the LiDAR, the other properties around the wavelength and the spacing and the pulse rate. Most LiDARs that we know today are rotating at about 10 hertz, so 10 times a second. And a lot of different startups are trying to differentiate on their software. So you'll hear a company called Septon, they call their product LiDAR, which has camera and LiDAR together. And AI is a Berkeley startup that is also have a camera embedded as part of the LiDAR. So I think to process the image, I'm not going to go into a lot of detail here. You'll have reference to that in the slides, so you can look at that. Let's look at some of the properties. So with light, you can get much longer range, and it will perform very reliably in a lot of use cases. Obviously, bad weather will affect light. So if you have a very heavy snowstorm or a sandstorm or fog or rain, the light will start reflecting back from these particles. But not all wavelengths. So certain wavelengths will actually pass through the snow particle or the raindrops, and you can still get good reflections. Field of view is obviously very wide if you're using 360 degree, and you don't care about working in the dark or not. Speed detection, you can get it to a good limit. So ultimately, we're strong believers that the best reliability is going to come from using multiple sensors. There are use cases where LiDAR is not going to be the only depth sensor that you use. Most of my work has been on autonomous vehicles, but there are a lot of other use cases where LiDAR just blows any other depth sensor out of the park, if you're not talking about just vehicles and robotics in particular. So some types of LiDAR that we've learned about, and this is not I didn't try to include everything, but those are the most well-known ones. Mechanical LiDARs have been the most popular, with Velodyne leading that. There is many manufacturers who are also doing mechanical LiDARs at cheaper price points. Solid-state LiDAR or flash LiDAR, you have these vertical cavity surface emitting lasers that you can put on a chip. It gives you better cost. However, it is lower range, and also because it's fixed in place, so what you get is basically these flashes of light. And if you're going at very high speeds, you might start missing things. But we're talking really high speeds. The light speed is much faster. But we've seen in our tools, when we help our customers with LiDAR data, if the car is moving and there is a very close object to you, in a mechanical LiDAR, you start getting a lot of ghost points where in the multiple spins, multiple reflections of light start showing up for the same car in multiple places. So instead of getting a point cloud that has a certain location for the entire car, you get this car and another ghost behind it and another ghost behind it. And that ghosting is just a function of the frame rate and the fidelity or the wavelength of the LiDAR laser that you're using. MIMS LiDARs are, instead of using a mechanical component, you use basically semiconductor to simulate the emitters to reflect the light into the directions that you need. So there are arguably more reliability benefits when you're using MEMS versus regular mechanics, especially for things like vehicles where you have to go over bumps and potentially get into accidents and things like that. So reliability becomes a concern. Flash LiDAR also does better on the reliability versus mechanical. And MIT released this where they're able to put this phased array on a chip that is so small. The range for these things is only 5 centimeters. So not sure about practical applications for that, maybe in surgery or very short range type of applications, but it's promising technology. And it is more complex because you need to coordinate all of the different lasers coming out. Mostly what we've seen, people have one laser beam and they have a splitter that splits that light into this phased array approach. Others have tried to have actually multiple laser sources, but synchronizing them and coordinating all of it becomes a huge hassle. Cool, so use cases, most of the autonomous driving companies today are actually not using LiDAR for perception. Most of them are using it for HD mapping and localization. And what they do is they go offline, collect tons of LiDAR data, form very dense point clouds of the streets that they want to drive in. And then in the production vehicle, when it's driving, it tries to compare the points the point cloud is generating as it's driving to the point cloud that is stored on the vehicle. And they use that to measure the deltas to see if am I really on El Camino? Am I really on 101 next to this intersection? Because GPS has very, let's call it unreliable certainty. And it gets really bad when you're in urban areas. And also for autonomy, because you care about the lane that you're driving in, GPS can never give you below 5 meter accuracy. And within 5 meters, you could be on another lane, right? So LiDAR really helps with that. And so what we've seen many companies do to create the high-definition maps is, like I said, they drive multiple vehicles in the same route to collect very dense point cloud. And then they try to recognize any dynamic objects, pedestrians, cars, moving or parked, and take them out of the point cloud so that they generate a ground truth representation of what the world looks like. And then they use that ground truth representation to localize or to measure against the point cloud that is being collected on the car in real time. So it's a sample of all of the dynamic objects that need to be removed in this scene and to generate it. So for perception, if you heard of the Uber accident, the LiDAR did actually see the lady, and just the software didn't think or didn't register that the lady is a human being. And because of that, let me keep driving. You get loss of life, probably almost killing the industry. Like, that's actually my biggest worry, is that if our president wakes up and says, oh, you know, we don't want another accident, screw these autonomous vehicles, we don't want any of it running, and that scares me. So perception for LiDAR is actually super critical. And a lot of people have been using clustering algorithms for the point cloud to try to understand the different classifications of objects. So is it a human being, or is it a car, or is it maybe a truck, or et cetera. And some of these things without camera are very, very hard to get. But a lot of it, also with LiDAR, you can at least guarantee that you can know the depth and the shape of that object. So in here you can see the cars, some pedestrians, and some trams in the image. With perception, also tracking and prediction are very kind of difficult problems to solve. You need to understand over multiple frames whether these 3D objects are moving or not. And once you determine that they are moving, you need to determine if that blob of points is the same blob of points that was moving in the previous frame or not. And so that requires you to have a unique ID for the prediction that you're doing. So like for that pedestrian, we call it pedestrian 7. And over maybe the 1,000 or 2,000 frames where that pedestrian is showing, you want to have that consistent ID and train your networks or your clustering algorithms on that type of labeling. And like I mentioned, like LiDAR is great, but sometimes you really need camera. And like in this case, you're getting a bunch of reflections from that pedestrian over there. But if on this street specifically, you don't really care that much about the pedestrian cutting the street. There's a barrier preventing them from doing so. That's where the high-definition map can make your decision-making prediction much, much simpler. If I know that on this street, pedestrians are not allowed to cross, then I don't have to predict where that person is moving, right? And like a lot of it is science, but sometimes some simple hacks can help take you a long way. There's some more engineering that we can do. And again, if there are some classical computer vision experts in the room, with semantic segmentation, when you can cross-reference what you're seeing on the camera with the points that are being reflected in the LiDAR, that can give you very, very good accuracy of this. I'm seeing a car, that car is over there, that car is not moving. And maybe you even look at the radar to see if the object within that range has velocity of 0 or not, and things like that. So this is a video to show you, so this is in our tool to give an example of the tracking and the classification. So cars are popping up based on the range accuracy or the range certainty. Most LiDARs today, the highest range we've seen is around 250 meters. But at 250, you're really like getting very little number of reflections. And some vendors, if you use their best, highest end LiDAR, in order to see something at 300 meters, you need to get 1 point, to get 1 photon back, you need to send about 30,000 photons. So it's like very, very low ratio of what you get back at longer distances. And this is just showing you how the LiDAR annotations are reflected into camera, and that can help with, like I said, prediction, classification, and tracking. And kind of just to summarize or conclude, LiDAR gives you 360-degree visibility and very precise distance, and the accuracy can be, the resolution, the range resolution can be down to about 2 centimeters, which is much, much better than what you can get with any type of other depth sensors. There is a concern around the sparsity of the data. So remember, we talked about the beams and the field of view of the beams and the density of these beams. The sparsity can become a huge issue, especially at longer distances, which makes classification and detection much harder. It does get affected by weather. If you use the longer wavelengths that do not get affected by snow or rain, those lasers are really, really expensive. And cost, finally, is kind of the most common thing. Velodyne has made a lot of money in the process as they were launching their LiDARs, and they did a good job. It's great for localization and mapping. I think that's the most well-known use case for now. Tracking, detecting, classification with LiDAR data is happening more and more. If you look on the Kitty leaderboard for 3D object classification, you can look at a bunch of papers that were released recently for classification and tracking based on just point cloud data. And some of them actually use both point cloud and camera, and really good papers. The last benefit is that a richer output, so you can make better decisions. Barriers, mostly cost, weather, sparsity, and even though there are some good papers and the community is sharing more and more what they can do with point cloud, it's not as much as what you have in camera, obviously. So there is, we think there's a ton of extra work that can be done around that. And some resources, love to take your questions.
If you have questions, please line up at the mic over here.
Hey, thank you for the presentation, Jared. I have one question. I'm kind of imagining, let's say there is a cross-section and there's no signals, and there are a lot of cars using LiDAR. What about the interference between the cars? How would it affect the LiDAR quality?
Yeah, it's a common kind of problem. Essentially, there are multiple ways that you can solve that, either depending on the frequency or the different wavelength that you're using, or adding a signature. There's a couple of companies working on frequency modulated continuous wave type of LiDARs that can solve that problem like without any issues. There is a huge concern about basically malicious players trying to derail the autonomous vehicle, and that's an active field of research. So there are a lot of ways to deal with the problem. None of them is perfect, and there are a lot of ways to hack it. That can be a topic of hours of discussion.
Good afternoon. My name is Ed Royce, and I'm with SocioNext. So I had related questions, but one of the alternatives that I was going to suggest to interference was coded pulses, but then you'd have to decode the pulses. But okay, I was going to ask about how much of an issue you have with multipath reflections and also with shadowing, and kinds of mitigation tactics you can use for those.
Okay, so when you say multipath reflections, is that for like mirrors that are reflecting multiple things, or?
Yes, reflecting off of windshields on multiple cars and back into your detector, that sort of thing.
Yeah, it's that's all software. It's like your receivers will get it, and you need to run a lot of filters and like signal processing on making sure that you eliminate the noise. It's never perfect, but it's good enough. I don't have a great answer, no silver bullet.
Oh, okay. It sounds like one of my hardware technicians in a former job. He used to ask in an exasperated voice, but it's only software.
Thank you.
In current autonomous vehicles, is the entire burden of object classification on the image system, or is anything done by the LiDAR right now?
It depends on the vendor. There are multiple customers we're working with that are using the depth sensor technology, not necessarily just LiDAR, but they're using depth as the major driver for classification. There are 2 or 3 companies that come to mind that they say they're camera first or vision only type of companies. The thing is, camera, like we saw in that matrix over here, it doesn't really do well in bad weather and in the dark. And even if you use an infrared or thermal camera, then that means more parts, more cost, and more processing that you need to add to the vehicle. And even if it's a stereo camera, actually, the depth from stereo, like a lot of people in research look at it as it's a solved problem, but actually stereo depth has a lot of issues on its own too, because you need kind of some feature anchors to enable you to get the depth accurately. So if you wanted to get the 2 centimeter kind of level of accuracy, I think light is kind of the best physical technology available for that kind of thing. Ultimately, we think for level 4, where you don't have a human taking any control of the vehicle, you cannot get away with camera alone. Tesla and others don't believe so. I guess I'll be proven right in a few years.
Thank you.
No problem.
Yeah, my question is more along, other than, great talk, by the way. Other than self-driving cars, where do you see the most prominent applications of LiDAR in the next few years? And also, second, can you comment about Quanergy and all the new startups other than Velodyne who are coming into the space and what impact that might have?
Sure. So I'm biased because Quanergy is a customer, but the applications, like I said, geospatial has been there for a very, very long time, and it continues to be that, right? So even satellites have LiDARs, and they use them for all kinds of things, even for like tracking economic activity. Military has been using LiDAR forever, and they will continue to do so. But now, most recently, Quanergy actually is looking at the security use case a lot more. So they're putting LiDARs to detect activity in deserts and things like that. And potentially even in urban areas, we're going to start to see more LiDARs to better understand consumer behavior. So not just around security use cases, but things like if I put a LiDAR in the Safeway aisle and I want to understand foot traffic better, that can give you much higher accuracy and richer data sets. Yeah, I guess like we can go on and on. I think the economy of using a LiDAR, once you can bring the cost down significantly, you can open a lot more use cases. But there is a huge barrier because of the cost right now.
So in short, there are many applications where the 2D alone is not enough and the depth will make a big difference.
Absolutely. Yeah.
I have one more question. This is about the noise. What are the typical noise models used in the LiDAR measurements, and what's the range of the noise that you see, and what kind of algorithms in software you guys use to filter out those noise or deal with the noise?
Yeah, it's Great question, but unfortunately, I'm not the right person to answer it because like we do software and AI. I can refer you to my CTO after the talk, and he'll be a better person to answer.
All right, I have one quick question. So Tesla had a very famous failure with a white truck fooling the depth
Yep.
sensing. Does LiDAR have a similar problem with either a material that absorbs that particular wavelength or a mirrored surface where they don't see anything?
I cannot absolutely say that LiDAR will not have a problem with it, but a lot of stars have to align for the LiDAR to miss something like that. Like the material, the type of LiDAR that you're using, the wavelength of the light that you're using, the software that you're looking at. And if you're not using sensor fusion, like if you're not looking at radar, LiDAR, and camera together, then if all of these stars align, then yes, that can happen. But we're engineers, like, yeah, I don't design my building to withstand meteors, right? It's because the probability of that is very small.
Yeah, but the Tesla knew in advance that a white wall would not be perceived by their depth sensor, but still.
What happened with Tesla is one of those edge cases where the radar also, essentially they didn't have any sensor looking at above the vehicle, and that radar was getting light. There's vacuum. There's nothing in front of me, and that truck was high enough that the white surface of the truck didn't reflect any radar waves, and the camera, thought that it's part of the horizon, depending on the sun angle at that moment. So, yes, I think they should have been using a LiDAR. If they had a LiDAR, it probably would have helped reduce the percentage or the probability of actually not detecting that object. And again, ultimately, that gentleman talked about software, but ultimately, if your software doesn't perceive it as a barrier, all bets are off.
Yep. All right, any other questions? Well, thanks again.
Thank you.